Okay, today's lesson is going to be on another integration method called partial fractions. And so, once again, we want to kind of talk about when should we use this particular method. And what I can tell you is that if you have a quadratic in the denominator, that will factor. So that's the important part here, is that the quadratic in the denominator can be factored. We're going to think about the possibility that it might be partial fractions. And so we're going to have to learn how to do a partial fraction decomposition. And so you might remember in Algebra 2 that you had things like, and I'm just going to put sort of an example up here, you might have had something like 4 over x plus 2 plus 3 over x minus 5, and you were expected to write that as a single fraction by finding a common denominator and doing a bunch of different things. And a partial fraction decomposition is basically going backwards from that particular process. And so what we're going to do here to do this partial fraction decomposition is I'm going to rewrite the integrand, 4x plus 41, over, and I'm going to go ahead and factor the denominator. So x squared plus 3x minus 10 would be the same thing as x plus 5 over x times x minus 2. And I'm going to set this equal to a over the first factor, x plus 5, plus b over the second factor, x minus 2. And my objective is to find the value of a and b. So in order to do that, what I'm going to do is I'm going to multiply this entire equation by both of these denominators, x plus 5 and x minus 2. Okay, so when I do that, on the left-hand side, both of those denominators are present, and so the only thing that's going to be left is the numerator, 4x plus 41, is equal to, when I multiply this fraction right here by x plus 5 and x minus 2, x plus 5 is going to drop off, and that's just going to leave me with a, sorry, I'm not sure why I wrote a 4, a times x minus 2. So a times x minus 2. Plus, when I multiply this fraction by x plus 5 and x minus 2, the x minus 2 is going to drop off, and so that's going to leave me with b times x plus 5. Now, what I'm going to do next is pretty clever, if I do say so myself. What I'm going to do is I'm going to allow x to be two numbers, one at a time, so that these two terms right here, this a x minus 2 and this b times x plus 5, sort of go away. And so if I look at this first term, a times x minus 2, I want to let x equal to positive 2 so that that term will go away. And so I'm going to plug x equals 2 into my expression here. And so if I plug in x equals to 2 into my left-hand side, that's going to give me 49. Equals to, if I plug in 2 to this first expression, that term is going to go away. And if I plug it into this term, I'm going to get b times 7, and I'm going to write that as 7b. And so that tells me that b is equal to 7. Okay, so now I'm going to let x be another clever number that is going to make this term cancel out, and that's going to be negative 5. So I'm going to let x be equal to negative 5. If I plug negative 5 into my left-hand side, 4 times negative 5 is negative 20, plus 41 is 21. And that's going to equal to, if I plug in negative 5 to the other side, I'm going to end up with negative 7a. And so this tells me that a is going to equal to negative 3. Okay, so now going back up to this first line in my partial fraction decomposition, I know that I can rewrite this integrand, and I'm going to do this back in black now, as the integral of, and I'm going to choose to put the positive term first. So because this b was a positive 7, I'm going to write that term first, and I know that b goes with my fraction b over x minus 2. So that's going to end up being 7 over x minus 2 minus 3 over x plus 5 dx. And so by doing this, both of these terms now fit the logarithm rule. And what you're going to find is that most of the time when we're doing partial fractions, these are going to fit the logarithm rule. So this will be 7 times the natural log of the absolute value of x minus 2 minus 3 times the natural log of the absolute value of x plus 5, and then plus c. And that will be my final answer here. Okay, on my next example, I also noticed that there is a quadratic in the denominator. And so my thought is that this could be partial fractions, but the first thing I'm going to check is to make sure that it's not a u substitution problem. So let's just choose u to be our x squared minus 5x plus our 6. That means that our du, based on that choice, would be 2x minus 5 times dx. Well, if you look at the numerator here, I have 4x plus 1. That is not a multiple of 2x minus 5, and so that's what tells me that this is not a u substitution problem, and so therefore I need to try something else. So I'm going to try to erase this u and du, and I'm going to try a partial fraction decomposition instead. Okay, so I'm going to take my integrand, 4x plus 1. I'm going to go ahead and factor my denominator, so that would be x minus 2 and x minus 3. And I'm going to say that that is equal to a over the first factor, x minus 2, plus b over the second factor, x minus 3. I'm then going to multiply the entire equation by both denominators, x minus 2 and x minus 3. And that's going to leave me with 4x plus 1, and I'm going to do this in black, is equal to a times x minus 3 plus b times x minus 2. And so again, I'm going to let x be two clever numbers. And so the first clever number is x is equal to 3, so that the term right here with the a will cancel out. So if I let x be 3, then my left-hand side is going to be 13, I believe. And my right-hand side is going to be b times 3 minus 2, which is going to be just b. Okay, so I know that b is equal to 13. Now I'm going to let x be equal to positive 2, so that this term right here will cancel. And so that's going to give me 4 times 2, which is 8, plus 1 is 9, is equal to a times 2 minus 3, which is going to be negative a. So that means that a is going to equal to negative 9. And I know that b is equal to 13. So once again, just for simplicity purposes, I'm going to write the positive term first. So the positive 13 for b means that I'm actually going to write this fraction first and then the a fraction second. And that's just out of simplicity and preference, really more than anything else. So this is going to be the integral of 13 over x minus 3. So make sure that you're careful to put the 13 with the term that had b in it, minus 9 over x minus 2. And so we see, once again, just like in example 1, that this now fits the logarithm rule. And so I'm going to have 13 times the natural log of the absolute value of x minus 3 minus 9 times the natural log of the absolute value of x minus 2, and then plus c. Okay, this next example already has the denominator factored for us, and when that's the case, that's like a huge indication that this is probably a partial fraction problem. So I'm going to start off that way and do my partial fraction decomposition. So 1 plus 3x over 1 minus x and 3x minus 5. And I'm going to say that this is equal to a over 1 minus x plus b over 3x minus 5. Okay, so once again, multiply the entire equation by both denominators, so 1 minus x and 3x minus 5. And when I do that, I'm going to get 1 plus 3x is equal to a times 3x minus 5 plus b times 1 minus x. Okay, so letting x be a couple of really clever numbers, I'm going to first of all let x be equal to 5/3, and that's going to get rid of this term that has a in it, and it's going to leave me with the left-hand side and this term right here. Okay, so what we end up having is 1 plus 3 times 5/3, and so that ends up being, let's see here, I guess 6, and that's going to equal to the a term is going to go away, and the b term is going to be left. So 1 minus 5/3 would be negative 2/3 times b. And if I multiply both sides by negative 3/2, I'm going to get b is equal to negative 9. Okay, the next thing I want to do is let x be equal to 1. That will get rid of this term right here and will allow me to solve for a. So if I let x be 1, that means that my right-hand side is going to be 4, and my other side is going to be negative 2a, I believe. And so a is going to equal to negative 2. Okay, so it turns out that both of these are negative, and so I'm not really sure that there's any advantage to putting one before the other, and so I'll just start with a and then do b. So this is going to equal to, I'm going to do this down here so that I have enough room, the integral of negative 2 over 1 minus x, and then minus 9 over 3x plus 5. Now, this does fit the logarithm rule. However, it's not quite the same as the previous problems, because if you'll look at the denominators of both of these fractions, whoops, I didn't mean to erase there. If you'll look at the denominator of that fraction and the denominator of that fraction, those denominators have derivatives. And so these are going to be similar to u substitution in your head problems. So this is going to be negative 2. The constant there is just going to hang out in front. I'm going to leave some space and put the natural log of the absolute value of 1 minus x. And then because the derivative of 1 minus x is negative 1, I need something to cancel that out. And so I'm going to put a negative 1 right there. Minus 9, and I'm going to leave some space here. Natural log of the absolute value of 3x minus 5 plus c. And in order to have that be the correct answer, I've got to look at that 3x minus 5 and notice that the derivative is 3. And so in order to have that cancel out, I've got to put a 1/3 in the front of my problem. And so this would give me the final answer. I'm going to just have to go in here to have enough space. This is going to equal to positive 2 times the natural log of the absolute value of 1 minus x minus 9 times 1/3 is 3 times the natural log of the absolute value of 3x minus 5, and then plus c. So you're looking at a final answer right here. Okay, so hopefully you're paying attention and making sure that it's not a u sub in your head problem. Be very careful not to miss out on that particular aspect of this question. Okay, this next example is similar to our previous examples. We have a quadratic in the denominator, and we need to factor out an x. So this can be rewritten as the integral of 4 over x times x minus 8. And so that's what leads me to believe that this is a partial fraction problem. So I'm going to start with my 4 over x times x minus 8 and say that this is equal to a over x, which is the first factor, plus b over x minus 8. Okay, if I multiply the entire equation by those denominators, x and x minus 8, then that is going to leave me with 4 is equal to a times x minus 8 plus b times x. And so just like we've done before, we're going to let x be a couple of clever numbers. So I'm going to start by letting x is equal to 8. That will get rid of the a term. And so that means that 4 is going to equal to 8x, or 8b, I should say. So let me erase that and put 8b. Sorry about that. Okay, so 8b. And so that means that b is going to equal to 1/2. Now if I let x be 0, that will get rid of the term with b in it. And so 4 is going to equal to negative 8a. And so that means that a is going to equal to negative 1/2. And this is the first problem that we've come across where a and b are the same numbers. And I know they're not technically the same numbers. One of them is positive and one of them is negative, but they're at least the same magnitude. And so what that's going to allow me to do is write that 1/2 in the front of the integral. And that's going to make our problem a little bit nicer. So this is going to become, I'm going to put the 1/2 in the front of the integral. And then b was the positive one. So remember that b went with this fraction right here. So that means I'm going to have positive 1 over x minus 8 minus my a fraction, which was 1 over x dx. Okay, so hopefully that's not too confusing for you. Since both of these numbers were a half, I can factor it out and put it in front of the integral and not have to worry about it. Okay, so this will become 1/2. The antiderivative of 1 over x minus 8 is going to be the natural log of the absolute value of x minus 8. That does not have a derivative. X minus 8 does not, and so I don't have to worry about multiplying by anything in the front, by the reciprocal of anything, minus the antiderivative of 1 over x, which will be the natural log of the absolute value of x. Now, this is not how the question is going to look on the AP exam if it's a multiple choice problem. You're going to have to go a little bit further than this. So we're going to have to remember that there is a property for logarithms that says if I subtract logarithms, what I can do is divide their arguments. And so this is going to become, as a final answer, the natural log of the absolute value of x minus 8 divided by x, because of this minus sign here. That's why I do division, because of the quotient rule of logarithms. And then, of course, don't forget about plus c. Okay, so that's usually going to happen if a and b turn out to be the same numbers with either the same or opposite signs, as you're going to be able to use one of those properties of logarithms that you learned in Algebra 2 or in Pre-Cal to simplify the answer a little bit more using those properties. Okay, for our last example, I'm going to use this as an opportunity to preview a future lesson. And the reason that this is sort of a preview of a future lesson is because of the upper bound in this definite integral, which is infinity. And so we've never seen that before. That's going to be what we talk about in a future lesson. And this is a problem that fits a partial fraction decomposition. So I'm going to use that as sort of a way to preview a future lesson, but while also talking about partial fraction decomposition. Okay, so the first thing I need to do is I need to factor that denominator, and I need to see if it factors so that I can know if it's a partial fraction decomposition or not. So I'm going to start over here with 2x squared minus 7x plus 5, and I'm going to notice that I need the factors of 10, so the 10 is obviously from the 2 and the 5, factors of 10 that will add to negative 7, and so that would be negative 5 and negative 2. So this will be 2x squared minus 2x minus 5x plus 5. If I group together the first two terms, I notice that I can factor out a 2x, and that's going to leave me with x minus 1. And from the next two terms, I can factor out a negative 5. So I'm going to go ahead and do that, and that's going to leave me with x minus 1 as well. And so the factored version of that denominator is 2x minus 5 and x minus 1. And so that means, because this can be factored, that means it is a partial fraction decomposition problem. And so I'm going to go ahead and use a partial fraction decomposition. So I'm going to say that 3 divided by 2x minus 5 and x minus 1 is equal to a over 2x minus 5 plus b over x minus 1. And just like we've done in all of the previous problems, we're going to multiply this entire equation by 2x minus 5 and x minus 1, both of the denominators there. Okay, so that's going to leave me with 3 is equal to a times x minus 1 plus b times 2x minus 5. And hopefully by now you're feeling comfortable with letting x be these clever numbers so that we can eliminate some terms. So if I let x be equal to 1, then that's going to give me 3 is equal to negative 3b, which means that b is going to equal to negative 1. And then if I let x be equal to 5 halves, that will get rid of the term that has b in it. And so that's going to be 3 is equal to 5 halves minus 1 is 3 halves of a. And so that means that a is going to equal to 2. And so I'm going to go ahead and use those numbers in my partial fraction decomposition. Since the a is positive, I'm going to write it first. And this is going to become the integral from 5 to infinity of 2 over 2x minus 5 plus, or minus, I'm sorry, let me erase that and put minus, what do we have? 1 over x minus 1 dx. Okay, now because this upper limit is infinity, I can't really plug in infinity, so to speak. And so what we're going to do, this is sort of the preview for a future lesson, is that we're going to rewrite this using a limit. So I'm going to rewrite this as the limit as b, the upper bound, approaches infinity of the integral from 5 to b of that integrand, 2 over 2x minus 5 minus 1 over x minus 1. And so this is called an improper integral, and the way that we evaluate improper integrals is by using limits. Okay, so I'm going to write down here limit as b goes to infinity, and my next objective is to find the antiderivative of this integrand. So I have 2 over 2x minus 5. So I'm going to leave the 2 in front. And then I know that that rule is going to fit the natural log rule, so natural log of the absolute value of 2x minus 5. But because that inside has a derivative of 2, that means I'm going to have to put a 1/2 in the front. Minus natural log of the absolute value of x minus 1. And then we're going to evaluate this from 5 to b. Now, notice here I'm going to use a different color that my 2 and my 1/2 are going to cancel out, so I'm going to go ahead and disregard those. And just like I did on the previous example, I noticed that this is the difference of 2 logarithms. And so I'm going to take this opportunity to rewrite this as a single logarithm using the quotient rule because of this minus sign right here. Okay, so this will be the natural log of the absolute value of 2x minus 5 divided by x minus 1, still evaluated from 5 to b. Okay, so if I continue here, this will be the limit as b goes to infinity. I'm going to go ahead and plug in my upper bound, which is b, so that'll be the natural log of 2b minus 5 divided by b minus 1 minus the natural log of the absolute value, and I should use absolute value here instead of brackets, so absolute value, minus the natural log of the absolute value of, if I plug in 5, then that's going to be 2 times 5 is 5, minus 5 is obviously 5, over 5 minus 1, which is 4. Okay, and so now I want to take the limit of this as b approaches infinity. And so I notice that the only b's are in this fraction right here. This is a rational function, meaning it's a fraction. And so as I take the limit as b approaches infinity, what that essentially means I'm doing is I'm finding the horizontal asymptote of 2b minus 5 over b minus 1. Okay, well again, I'm looking here. I notice that that fits the eats DC category. And so the inside of this absolute value bar is going to evaluate to 2 since the exponents are the same, and I divide the coefficients. So this is going to equal to the natural log of 2, and I don't need bars anymore since I know that the absolute value of 2 is just 2, minus the natural log of 5/4. And on the AP exam, this would obviously be worth full credit, but if you wanted to go a little bit further, you could again use the quotient rule for natural logs. So 2 divided by 5/4, which is the same thing as the natural log of 2 times 4/5, which would be the natural log of 8/5. Okay, so that's your lesson on partial fractions. Let me know if you guys have any questions.